All right. So I'll talk to you about some, yeah, no, yes, okay. I'll talk to you about some work that we did when I visited AWS a while back, which essentially tries to tackle this question, which asks, why don't we have formal methods or verification tools in particular integrated into distributed system development? And I argue that to a large extent, this is because researchers and developers have different conflicting desiderata. So on the one hand, we have researchers that typically design powerful reasoning techniques, often for domain-specific languages. Prime examples are Spin, TLA+, and so on. And on the other hand, we have developers that prefer mainstream languages, and they don't care so much about the underlying technique as, rather about whether it integrates well with their workflow. Right, so what I argue we need to get verification tools into distributed systems development is techniques that work at the implementation level, so that developers do not have to learn new languages, that are fully automated, that offer some API for abstract modeling, and that they also offer some verification guarantees. And in this talk, I'll talk to you about MUST, which is a practical way to do model checking for distributed protocol implementations. MUST is a bounded model checking framework, and the key observation behind it is that protocol implementations typically consist of large, complex parts of local computation sequential code. And then there's just a small handful kind of a code that takes care of inter-process communication. So MUST essentially advocates for this design for a verifier, which has that take a mainstream programming language like Rust or Java, and this will do your local computation, and then have a lean concurrency API through which all inter-process communication will pass. Right, so as long as the code abides by this convention and all the inter-process communication goes through this API, then one can instantiate MUST for a given mainstream language. And in the case of MUST, in this concurrency API, which is where the model checker lives essentially, this is backed up by a declarative semantics, which is very tightly coupled with a dynamic partial reduction algorithm. And in fact, I can show you the API. It's these three operations. We have a non-deterministic choice among a set of values, a send operation, send to thread T the value V, and then a receive operation. And MUST is the first framework of its kind, like a dynamic partial reduction framework that has a number of features that are quite useful in modeling distributed protocols, like non-blocking receives, selective receives, and so on. And I'm going to go over these in the rest of the talk. But my goal is to convince you that this can be a useful tool when dealing with distributed protocols. So let me begin by talking a bit about the underlying formalization of the API. So in MUST, the semantics of a program is given as a set of graphs. And I have an example up there. This program has no local computation, but even if it did, this wouldn't show up in the semantics, right? So we have a thread T1 that sends a value to itself. We have T2 that essentially sends two messages to, whoops. Anyway, so it sends two messages to T3, and T3 just gets one of them. Now, the semantics of this program is a set of graphs. I have two graphs there on the right. The nodes in the graphs correspond to instructions, and then the various edges denote relations between the instructions. So this black edge there means that these two sends are ordered into the same thread. The green edges show which value the receives are getting. This is getting 1. This there is getting 2. So some comments about declarative semantics. The reason why we use declarative semantics is that it's flexible when talking about the underlying communication model. So for example, this graph on the right is inconsistent in some models. If we assume, for example, peer-to-peer communication, then T3 cannot read 2 before reading 1. Right? So this graph is not a part of the semantics under peer-to-peer. It would be a part of the semantics, as in this case here, if we assume, for example, asynchronous communication, UDP and so on. So this is one point. The other point is that this semantics is a partial order semantics. So for example, T1 does not interfere with the other threads. And so in the graphs, this node corresponding to this send over there doesn't interfere with the rest of the graph. There are no edges incoming, outgoing, and so on. And having this partial order semantics is useful because based on it, we can devise a dynamic partial order reduction algorithm. The way this works is that it verifies a given program by enumerating the graphs that are a part of the semantics. And I can show you a very small example. The procedure is essentially a depth-first search. So we start from an empty graph. We execute the program, and we add the instructions one by one. And whenever we're adding a receive, so here we're adding this receive from T3, we explore all possible options for the message that this receive can get. And of course, in this example here, the option above where it gets the value 2 will only be explored if this is allowed by the underlying communication model. So the DPR of must is the first DPR for message passing concurrency that is sound, meaning no false positives. It only explores consistent configurations. It is complete. It will explore all the graphs in the program semantics. It is optimal, no redundant work. And it's also parametric in the communication model and has polynomial memory consumption. This parametricity shows up in the API, so we can actually select the communication model under which we send and receive messages. OK. So now let's take a closer look at the features, starting with non-blocking receives. Non-blocking receives are useful when modeling things like timeouts. So for example, if a receive doesn't get a message within some time frame, then it might time out, and we want to be able to model that in our framework. And there are two ways to do this. There's what I call here a naive way, which we can do with the API as I've shown it so far. And then there's what must actually does, which requires enriching the API a bit. And I'll explain why must doesn't follow this modeling on the left. So I received the timeouts. We wanted to just return bottom when it times out. One way to do this is to use this non-det there. And if it returns 1, we do a blocking receive. If it returns 0, we can return bottom. So must does not do this, and instead it kind of changes the API a bit there, and it adds this attribute denoting whether the receive is blocking or non-blocking. And for non-blocking receives, we modify the semantics so that they can return bottom. And if we do this, actually we get a coarser semantics and a coarser model. An example here is this, where we have n threads just doing a non-blocking receive. If we have the naive modeling, then just to model all the combinations of the non-deterministic choice, we have 2 to the n graphs that we would have to explore in our semantics, and the algorithm would have to enumerate all these graphs. But if we have this kind of special modeling, then there's only one graph in the semantics, which is this one. All the reads are just returning bottom. There's no message that they can read from, and we can get away with just one graph. Right? So essentially, another thing that this framework is advocating is that this tight coupling between the semantics and the algorithm, and how to build the semantics that kind of favors verification. And there's a similar story for selective receives. So selective receives are useful for modeling things like versioning, communication closure, and so on. If there's a protocol that you can decompose into different rounds, then a particular round, you might want to get just messages designated for that round and not messages for previous or subsequent rounds. One way to do this is with selective receives. Again, 2 ways to do this. What we want is essentially some predicate in our receives saying which messages we should get. Now, the naive way to do this here would be to just do a receive, get the message, and then have some assumed statement that essentially aborts the exploration if the predicate that we care about does not hold for the message that we got. But must does not do this, and again, it builds this thing into the semantics. The semantics are aware of predicates. The reason, similar to before, is that this is coarser, and we have an example for that in the paper, but also more expressive. And I want to show you here why it's more expressive, because this is a bit more interesting. In this example, we have 2 threads. The T1 sends 2 messages to T2, and now T2 wants to receive them in the opposite order. in which they were sent. But note that this program here is assuming peer-to-peer semantics, right? So if we do the naive modeling, then as soon as we reach this first receive there, and if we follow this modeling, we'll do the receive, but then under this normal peer-to-peer, the only message that this guy can get is this one, and the assume will abort. So there's no full non-blocked execution that we'll get. However, if we change the model and we have the semantic support, then there is one full non-blocked execution that we get, which is this one, which is not expressible with assumes. And we essentially get that execution because we change the meanings of receives under peer-to-peer from, for example, very roughly, fetch me the first message from a given sender that's available to me, to fetch me the message from a given sender that's available to me and satisfies the predicate that I care about. And this is how languages like Erlang, if you've seen programs in Erlang, do this sort of receiving based on some clauses that they have. Okay, so again, the story here is that we modify the semantics. We make our receive statement like this, and if we want normal receives, like the way I showed them previously, we just make the predicate be true always. And the kind of final two features I'd like to discuss, which are related, they have to do with how DPOR works. And the issue is that DPOR typically only reasons about assertion safety for a given program. So it will just ensure that no assertion in the code is violated. But often, especially in this context, it is useful to talk about properties that somehow describe the state of the whole system. And I have a kind of a small example that tries to get this point across, which is just two threads sending some message to some other thread, doesn't matter which one, and we ask something like, is the send of T1 always executed before that of T2, which is somewhat non-trivial to express an assertion. And so Mus wants to be able to reason about such properties, and the way that this is done is by employing monitors, which are just some special threads that track communication in the system. And so in this case, if we want to reason about a property like this one, we would transform this program into something like this, where instead of just doing a send, we do a send notify, we notify TM. This is a monitor thread. And the monitor just gets two messages and checks whether the first one is the one sent from T1 to Tn, and the second one, the message sent from T2 to Tn. This property here that we care about does not hold clearly, but the point is that by having monitors kind of track this communication, we can reason about this thing. And now, so this is one kind of point. The other point that I want to stress is that if we look a bit under the hood and how these send notifies are implemented, these are just another send to the monitor, right? So this thread notifies the monitor about the subsequent action, and this one does the same thing there. But what's important is that this communication with the monitor needs to take place under a different model than the rest of the system. We kind of describe in the paper why that is. Very roughly, it's because if two notifications to the monitor are causally related, then we need to ensure that they'll arrive to the monitor in the correct order. And for this, we need a different semantics for the messages that are sent to the monitor. But this is actually possible in Must, and we can have multiple communication models coexisting within the same program, and not just causal delivery and peer-to-peer, but also asynchronous communication, mailbox, and so on. You can mix and match within a given program. Okay, and then I'd like to kind of end with some note on the practicality of this. So this is some case study that, again, was done in the context of AWS. We tried a handful of realistic protocols, and some of them were designed along with developer teams. And I just have two benchmarks here to make 2 points. The first point is that if we have selective receives, we can see in this benchmark it's the state space is exponentially smaller, so it does help, and it's kind of beneficial for both for modeling but also for verification purposes. And the other one is that even though monitors increase the amount of messages that are sent in the system, they do not increase the state space exponentially. They increase it just a bit, but it's still manageable. Right, so hopefully I convinced you that this is a useful framework, and I'm very happy to take your questions and feedback.
Right. If anyone has any questions, step up to the mic. Now is your chance. Okay. Maybe I can try and get something kicked off here. So one thing that I was wondering is how do you actually build these models? Are you dynamically executing the program and constructing the model on the side and then model checking that? Or is this a static process and then you do model checking on?
You mean as in how do we do the verification essentially? Or?
Yeah.
Yeah, so it's a dynamic thing. You repeatedly execute the program. Maybe I can go back to this example in the beginning. So this exploration. So what you do is that you execute the program one instruction at a time, right? So you execute this, you make this in your graph. So you make the graph bigger. Whenever you have a choice, like here, for example, there is a choice, you go with one of them and keep executing. And then when you finish completely dynamically executing the program, then you restrict the graph. So you would get, like if you end up with this state, you would restrict it to this thing. You have some marker that you have some work to do. And then you use the restricted graph as some guidance for the runtime and re-execute the program from the beginning. And then try the alternative option to see what happens. So essentially this guidance part, if you have receives in this cut graph, then the model checker informs the runtime of the value that this receive should be reading.
Gotcha. And so you're actually model checking like LTL properties, or what's going on under the hood there?
No, there's no LTL. The properties that are expressed, for example, with these monitors are as special processes that kind of track what you want.
I got you. And so like a verification failure would be one of those monitors sort of.
Right, exactly. It would be, yeah, exactly.
Yeah, makes complete sense.
So how does this work with the non-determinism in the local computation part, which might affect which messages are sent and so on? Do you assume every non-det thing calls your...
Yes. So the dynamic partial reduction kind of by default assumes that there is no data non-determinism. If there is, then, which we have in this framework, it needs to go through this API. Yeah.
Can you pull up the slide where you talk about how you're exponentially shorter than other approaches? Yes,
this one,
the naive versus must.
Yeah.
So I didn't fully understand why allowing it to provide to return bottom in the way that must does it is different. And can you say a little bit more about that?
Right. So the point is how many graphs you have in your semantics, and if you have this non-det, then this, I don't have the graph here, but this will show up in the graphs.
I understand why the non-det has 2 to the n, right? What I don't understand is why the same example in your system only has 1.
Right, so there's no non-det, right? So it's just that you treat this thing as a built-in, and there's like some attribute that says that this is non-blocking. And so if you had an exploration like this one here, so here, for each of the sends from which you can read, right, you try, there's a different graph. And then you would add to all these sends a bottom option, right? So it's just some, like some special node, you can imagine some special node in the graph from which non-blocking receives can read. But in this example here, since there is no send, there is no nothing, right? The only message that these receives can get is bottom. So it's just that there is only one consistent graph in the semantics, and this is what you explore.
Oh, okay. I guess right. So this is under the condition where there's no sends.
Yeah. If there is a send, then you'll also explore. This receives reading from that send.
If I have n sends, then I'll still get multiple.
Yes. Yes.
Although maybe I would get n if I had n sends and.
If you have n sends, well, to which process are the sending the message?
To the one that's receiving.
Because here I have multiple ones, right? Multiple parallel processes that do the receive. If you have a single process that's receiving n messages, and there are n different ones, for example, that send, then you may have even like quadratic, whatever. Yes, n options for the first one.
I see. So you can get 2 to the n. If the graph is just this way, but the point is you can optimize it if you don't have.
Yes. So you just optimize in some cases. Yes.
Yeah. Okay. Thank you.
Let's thank our speaker again.